Hello, viewers. We are live right now, and with me today, I have our guest, Mr. Peter. He is expert in designing PCB from the KiCad tool, which is an open source tool. And why I have this session today, because in VLSI we make chips, and the chips, to reach the end user, it has to land on the PCB. If that it doesn't land on the PCB, you cannot get a chip in real time usage. So when you are end user, you are using a device, it has to has a PCB inside. Even from outside covering you cannot see. So every chip has to finally land on the PCB, and that's why PCB holds a very important part in the bridge, like a bridge that chip crosses to reach the end user. And if there is no PCB, no VLSI chip that is reaching out to the market and to the end user. So this is very simple and straightforward. So over to you, Peter. So can you introduce yourself, share your professional journey, and identify with your own words for our viewers?
Thank you. Thank you for the introduction, Mridu. I am working, or I've been working as a hardware design engineer for about 20 years with some rest periods because I switched companies. So for a limited time, I wasn't in the hardware design area, but let's say for 20 years. And for the last 7 years, I've been freelancing. It means working on my own. I am a contractor for companies that don't have a hardware design engineering team or does hardware engineering design team, but such companies don't have enough capacity, so they hire me for a project or two. So I would help them to finish the project or to work on the project on my own, like a single engineer. And then after finishing that, they switch the manufacturing data into manufacturing, and I will help them with the testing or yeah, mass production introduction. So yeah, that's about me.
That's great. So having an experienced person from the PCB background helps our viewer to know about the PCB. So the next explorative question to you, Peter, is that over the last 20 years, how many generations of advancements the PCB manufacturing industry has experienced?
Yeah, yeah. The last 20 years, I think, have been very fast in development and in changes. The, let's say, a few words describing those 20 years are miniaturization and multi-layer boards. Because from the big THT components, we went into SMT. It means surface mounted components, which are much smaller. Those components take much lower PCB area, yeah, and allows us to design so-called high-speed design boards. It means it allows us using the latest CPUs, memories, video processing units, cameras, sensors, etc. So miniaturization in the 20 years was the main topic. And then I can say that automation in manufacturing was the second big area, second big point. In the manufacturing of PCB, there are technologies like machine learning, because during the production, we are using the image processing units that help us with verification of the manufacturing, and it higher the production yield and yeah, makes the efficiency of the manufacturing much better than before.
Yeah, great to know about that. So with me, I have a reference of my from my own collection. This is, you can see, this is a very old PCB. So it is from the 90s, and I am preserving it for 30 years. So I was an enthusiast. That time I used to make circuits using these PCBs and solder the components and make this. So Peter can easily relate that this PCB, whatever PCB is made now, do not look like this. So he might have something with him or maybe he shares a lot of pictures of the PCBs through his LinkedIn handle. So PCB is something that is very essential when a chip goes to the market and reaches the end user hand. With that context, we will move to the next question. Is that can you walk us through the physical process of how a PCB is manufactured? Also, what tools and softwares commonly used to design these PCBs?
Yeah, thank you for that question. That's an excellent question. I start from the designing process. Now, let's say we have to sit at our computers and use some EDA, so-called EDA tools. It means tools that allow us to create the schematic and the PCB layout in our computers. The most used systems are KiCad, as I use it, or Altium Designer, OrCAD, Cadence OrCAD, or Siemens Expedition. I think those four play the main role in the PCB designing area. Then, when we so-called export manufacturing data from our EDA tools, typically we send the manufacturing data to the PCB manufacturers. And the manufacturing guys process the data like they have to process the data. They have to print the data. They have to transfer the digital data into the physical format. So they print the, let's say, the tools that allow them to manufacture the PCB, because the following operation is etching. It means the printed layer on the PCB substrate using the photolithography process must be etched, and after that there are drilling of vias. It means the holes for interconnection between layers, and the second or the third step is layering. It means that those layers are laminated together. Typically, these days, we have multi-layer PCBs, not only two-sided, like you showed before. We have multi-layer PCBs, typically 4, 6, 8, or even higher number of layers we are using today. So they layer like a sandwich, layer the layers in the sandwich wise manner, and then the final operations are again the drilling and the plating, because as I said before, we can have the holes for vias. It means for interconnection between inner layers only or through the entire PCB. So there are multiple drilling and plating processes, and one of the last processes is the printing of silk screen. This is the layer of labels and description of the PCB. It means typically the reference designators for components. It means R1, R2 for resistors, D1, D2 for diodes, etc. And the testing. Testing is always the last step in the manufacturing, because all good, and I believe absolutely all PCB manufacturers test our PCBs before shipment to the end customer. And the testing contains testing against short circuits, conductivity tests, and optical testing. So those steps are performed during the PCB manufacturing.
Good to know. And you have expertise on the KiCad software, which is a FOSS software, and yeah. So that
The KiCad.
you use. Yeah, you can share some details about that KiCad.
KiCad is, I don't know how long it's been developed, but I think about 20 years. It started in Switzerland, in a CERN Institute. It's you maybe heard about that. It's the institute of, there are some high tech technologies around that, and engineers at CERN started designing their own system for PCB designing, because they were not satisfied with the systems at that time. So they started writing KiCad from zero, from scratch, Now we are using the version number 8, and I believe in a month or even shorter time, the version 9 will be released. And I can say that even this version 8 is fully competitive to the other systems when we are speaking about complexity of the boards that can be used for majority of designs. I don't say that we can use KiCad for designing, for instance, PCBs for mobile phones or high-tech PCs or AI processors at NVIDIA, etc. But majority of designs can be easily designed using KiCad because the complexity is fitting the KiCad performance and features.
Yeah, great to know that. And for those, I think for the industry, for mobile phone boards, and for that, I think industrial simulators and the setups, they will be needed. Great to
Yeah.
know.
Definitely
Version
simulators.
when see you said that version 9 is upcoming, that means it has crossed a lot, and a lot of things have been implemented and fixed, and version 9 for a FOSS software is huge, is huge.
Yeah. One of the upcoming new features is the support of ODB++ format, which is the modern format for transferring manufacturing data. Up to today, we are using the Gerber files. Those are so-called ASCII files or Gerber files. This is text format files, which are only like renders of each PCB layers. But the ODB++ format contains even the interconnection information and information about components. So it's much easier for the PCB manufacturer to process the ODB++ format. And I'm happy that KiCad number 9 will be supporting this format in version 9. So yeah, this opens the entire new area of usage of KiCad because some companies, as I know, don't use KiCad because of lacking this support. But version 9 opens the new door for the ODB++. So
Great
I'm
to know.
very happy for that.
Great to know that, because whenever something is coming in these areas, right? And
Yeah.
I have not explored the KiCad yet. And is there anything like having plugins or etc. for KiCad? Is there a developer community?
Yes, I think there are a few communities around KiCad, the solo developers or even when teams of developers, and we can find plugins for manufacturing, for major manufacturers develop their own plugins, so you can install the plugin into KiCad, and one click you can send the manufacturing data into the manufacturing system. So it's very easy. There are rendering 3D rendering plugins, so you can easily export your 3D render into, for instance, Blender, which is the 3D modeling tool, and you can then create perfectly looking 3D renders of your PCBs, which is great for manufacturing, for presentation, documentation, etc. So yeah, there are a lot of plugins and all are open source. So yeah, the whole system is open and everyone can write their own plugins using Python. Python language is used for the plugins.
Great to know, because today nowadays the Python is having the lot of flexibility. Even say in VLSI, in the front end, in the verification part, the Python is hugely used, and I have covered a series on Python 3 in my channel. But however, Python is not only limited to that. Python is today explored in every possible way, and Python is growing very fast,
Yeah,
and its
yeah.
acceptability is huge. Recently I was coming across some GPTs. They can actually interact with the APIs of the well-known GPTs through a Python interface, and
Mm-hmm.
can be used to desktop. My exploration is not finished yet, so I cannot share the details, but Python is way more expansion than any language. and
Yeah.
in any plugin kind of thing. So it's going in a huge fashion. Even EDA
Yeah.
tools do have Python interfaces where the EDA tools can interact through to the design through the Python. So yeah, after Tickle. So Tickle is for the backend design, but Python is for front end design. But Python do have a interface, couple of EDA tools, and that's why Python is paving its own way and going through crossing every barrier that seems to be there, and it is crossing every barrier. And great to have even Python. Seeing, I am very much happy, excited to see that even Python is in the PCB design also. So it's great to see.
Yeah.
Great to see that.
I'm very happy that KiCad supports the Python because, as you perfectly described, Python is a modern object-oriented language and easy to use even for non-PCB designers. Yeah, so it means that KiCad can be used not only by PCB designers but as well by software engineers because we need new plugins, we need support for new technologies. AI is coming from every direction, so I think software engineers are very welcome to contribute on KiCad development.
Yes, and that will be very about this open source software, and AI is getting into the open source softwares also, because for audio edits I use Audacity, and Audacity already have a plugin, AI plugin into it. I just came across last week. I am very much excited because even the open source softwares will have a taste of the AI. Red Hat is also building a enterprise version of of its AI version. So I came across very recently in last week. So I have another podcast which is called the TSA podcast. In there, I go solo and I share about this latest news. If viewers are watching that, they will come to know. And with that note, we'll move to the next question. That when did the transition from bulky components to the surface mount devices take place, and what drove this shift? Before answering, I'll show the viewers that I have this PCB. I'm an electronics enthusiast, and I have this with me from the 90s. So this board, if you look right, all the components are bulky components. You have big capacitors, and nowadays these are getting replaced by surface mount devices called SMDs, and even this circuit will shrink, maybe it's half of the size nowadays if it is designed. uh, so talking about the surface mount device, question to you I already asked, so you can go
Yeah.
for that.
Definitely. I think this shift began in the even in 80s with the needs for miniaturization and uh, with needs for high-speed designs. So I think it started in 80s, it continues and gained the momentum in the 90s. But in the last 25, 20 years, the majority of designs use the SMT only components, but it doesn't mean that the THT or the bulky components are obsolete and not used anymore. There are some areas that we still need those big components, for instance, the power electronics, audio electronics. In audio electronics, there are still a lot of designs based on THT or the bulky components because they have some special parameters. Yeah, the miniaturization takes its price. The price is some parasitic parameters. So yeah, there is some balance between size and performance. So yeah, 80s to 90s, and let's say 95% of designs are based on SMTs, but there are still very niche segment of THT designs, and I think it will last for a very long time. There is no visible end of the THT components.
Great to know about these facts, and with that note we'll move to the next question. uh, uh, do you see that the bulky components will get obsolete very soon, or they
Uh,
will continue to coexist along with the modern technologies for next few decades?
yeah.
So
Yeah, I believe they will coexist, the THTs along with the SMTs. because as I described, there are advantages on both sides in both families, so they will coexist. But for the, let's say, wearable technologies, wearable devices, mobile phones, PCs, computers, SMT only, but power electronics, audio electronics, and some special electronics, for instance, in automotive, there are still bulky components, and it will be for a long time.
Great to know. Great to know about that. So one important factor when AC adapters would earlier, there used to be a step down transformer. So how its picture now is that is totally gone or it is still existing when you design or see your designs around you, or maybe with your experience more than a decade long or maybe 2 decade long experience, what do you see? The transformers are totally gone or they are still existing in some places?
In my opinion, the traditional big iron core AC transformers in our AC adapters are almost completely gone. The traditional low frequency transformers are or have been replaced with the switching mode power supplies with much smaller transformers with the better core materials. The switching frequencies are typically between 100 kilohertz and 2.2 megahertz, while the traditional transformers work with the mains frequency, which is 50 or 60 hertz. So yes, I think it's almost completely gone, and I don't think that you can find a modern AC adapter based on the transformer or the traditional transformer.
Correct. That is a very good information because this step down started a long back when people are using electricity to power up the electronic circuits, and now the
Yes.
AC adapters going, as you have said, in the smart power supplies are getting designed and they are completely vanished. So
Yeah.
good to know about that. And with that note, we'll move to the next question.
Okay.
How the quality assurance in PCB manufacturing is ensured
Mhm.
for a reliable quality and performance. That means we have a PCB manufactured, right? But how that
Mhm.
quality check, that means that PCB is good, the interconnection is good, it do not have any breakage or anything like that. How that quality
Mhm.
checks is done? What quality checks are done? Yeah.
Yeah, that's an excellent question because we need to take care about the quality of manufacturing because the, let's say, bad quality means wasting of money, and no sane manufacturer wants to waste, yeah, money. So yeah, naturally. So those technologies are automated optical testing in manufacturing. This is the technology based on the machine learning. You can imagine that you compare the sample image with the current image of the PCB being manufactured, and the computer compares the wanted result with the current PCB assembly. So the so-called AOI, or advanced optical or automated optical inspection. The second technology can be X-ray, because as I described, there are multi-layer PCBs. So the optical testing can be used only for surface layers, top and bottom layer. But the inner layers must be checked only with X-ray. So X-ray scanners and X-ray yeah, inspection devices. The electrical testing, this is for both inner and outer layers. It means that the checker tests the conductivity and checks for the short circuits of the tracks and other areas on the PCB. And the last one, for instance, for yeah, especially for PCBAs, it means the PCB assemblies are so-called environmental tests. Those tests are based on the uh, ramping and stepping down of the humidity and temperature. So you close your PCB assembly into a chamber, and the chamber automatically step up the temperature and humidity and checks from minus, let's say, minus 40 degrees centigrade up to 100 degrees centigrade and from 0 relative humidity to almost 100% relative humidity. So those tests test your devices in very harsh conditions of low temperature or very high humidity. So those for optical tests, X-ray, electrical tests, and the environmental or the temperature/humidity tests.
Great. So this much of testing goes before the PCB comes to your hand, or that hand in a designer who has designed the PCB.
Yes, especially the first three tests, the AOI and electrical. I think 100% PCBs are tested optically and electrically. If you want, PCB manufacturer would test your PCB with X-ray, but of course those testers are very expensive and those tests are usually charged with some extra money. And the humidity and temperature tests are as well charged with some extra money. So let's say standard price covers the optical and electrical tests, and extra money are paid for the X-ray and the environmental testing.
Okay. So understood. So it's like package.
Yeah,
Got it. Got it.
yeah. You agree with the manufacturer on your package, and they will charge for the work done on the PCBs.
Great. Great to know. And once you receive the PCB in hand, before soldering the components, what steps you take? Is there any step today to do that?
You mean I, as an end user of the PCBs, as a designer, when I
Yes.
receive the
Yes.
PCBs? Yes, uh, definitely. I optically check the PCBs. I look for the missing components or wrongly soldered components. Even if the manufacturer used the optical tests, I always recheck the PCB assemblies for some missing or bad soldered components or some short circuits between very, let's say, fine pitch connectors or components that are close together. So I need to verify that the PCB assembly is perfectly soldered. Then I use a simple methods for verification that there are no short circuits between, let's say, input terminals, between plus input voltage and the ground. I check there is no short circuit, or even at the output, or yeah, the typical PCB contains a lot of so-called test points. Test points are the exposed copper areas where you can put your probes, and
Okay.
between two or more points you can check the electrical parameters like conductivity, or in the running PCB the voltage or current flowing between those points. So those are the typical steps I use, and I believe all engineers use for the prototype testing and yeah, powering up the new coming boards.
Great to know that. And once you receive, I think you receive first a PCB prototype on your hand, and then the final one once you confirm, right? Is like
Yes,
that a process?
yes.
Okay. So another question is that all these tests, when you do right after that, you get a final version of the PCB, and once you get that, do you get that all components ready in the board, or you have to manually do it by yourself at that?
Yeah, that's a good question. Usually, I have to solder the components that are uh, missing on the PCB, and the fact or the reason why the components are missing is that those components were on stock at the time of ordering the PCBs, and to make the process quicker, I agreed with the manufacturer that they will not assemble those components, and I will solder them after receiving the PCBs, because in the meantime I ordered components, and yeah, those processes are going in parallel. So the PCB manufacturer manufacturing the PCB, and I'm ordering the missing components. Or for the temperature sensitive components, the processes using when manufacturing the PCB assemblies are not compatible with those temperature sensitive components. So the temperature sensitive components can be, for instance, the very sensitive optical sensors like yeah, all kind of sensors with very, very precise and thin plastic layers. It can be even some kind of LEDs. Even some kind of LEDs are very temperature sensitive, and they are not compatible with reflow soldering, which is the typical technology used for soldering the PCBs. So those are two reasons why I always have to finish the assemblies with the components that were incompatible with reflow process or simply missing at the time of the manufacturing because of the manufacturing of the not yeah, they were on stock on the on the
PCB manufacturers, right?
exactly.
Yes, got it. Like you said about the devices, that LDR is also a kind of device, optical device that needs input from the remote control devices, right? So is that also is vulnerable to the temperature or something like that? I'm just sharing my views. Whether it is true or false, you can share.
Yeah. Each component today, and I can give a piece of advice that if you can't find a data sheet or a good documentation to the component, don't use it because yeah, simply said, don't use it. So all good components from good manufacturers have documentation, and in those data sheets is a section of soldering, and there is a recommended soldering profile. It means the temperature profile for soldering. There are some phases like preheating, heating, soldering, cooling, etc. So those are especially the maximal temperature that the particular component withstand. And there can be issue because if you use bulky components on the PCB, those bulky components takes time or higher temperature to be proper soldered. But those small plastical and very sensitive components wouldn't withstand the temperature needed for soldering the big and bulky components. So it means that you have to solder them after that, after the soldering process, because the small components, the sensitive components, wouldn't withstand the high temperature needed for soldering of the big component. So yeah, this is the simple reason.
Okay, so another question: when a PCB is manufactured, right, the boards, they have any kind of temperature tolerance, the boards itself, or there are variants of boards for different temperatures, or maybe like that? Can you share some lights?
Yeah. There are a lot of materials used as a substrate, so-called substrate for the PCBs. The substrate is the layer between. Yeah, you can imagine the simply said two-sided board, top layer and the bottom layer, and in between there is the electrical or the substrate layer, and this is made out of some glass layers mixed with some other materials, and those substrates have melting points. And during the manufacturing or during the operation of the board, you can't overreach or go over the melting point because the PCB then loses the rigidity. Yeah, that became flexible, and they are dangerous. There is a danger or risk for bending or twisting the PCB. So the typical melting points for low-cost PCBs is about 130 degrees centigrade. There are high quality materials, so you can go up to 250, let's say, degrees centigrade. So in between 130 and 250, there are areas for melting points. And each PCB manufacturer verify the manufacturing process, and when they found that the PCB you chose for the order is not compatible with the solder process, they advise you to use the, let's say, more expensive, yes, usually more expensive, but higher quality material to
Yeah,
avoid
that is
to avoid
yeah,
bending,
that's
twisting,
a great
etc.
information you have shared. That's a great information because when we say PCB, we say PCB, but there are some underlying facts
Yeah,
that when during manufacturing they could be of different grades, different temperatures, and heat sensitivity. It's a good
Yeah,
thing to know.
yeah. I forget one thing, that even we, as the PCB engineers and designers, can influence the temperature performance. For instance, if you use the copper polygons on the PCB, let's say imagine top layer of the PCB, and there are some copper polygons. Those are, polygon is an area of copper, not track, but the bigger area on the PCB. And you can, or you have to, equally distribute the copper on all layers, because when you inequally distribute the copper, then during the manufacturing, the 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 area on the PCB without copper is being heated more like faster than the areas with copper. So it means that those imbalance with the rate of heating causes bending and twisting. So we as PCB designers have to take care about the copper areas and think in advance for the manufacturing process. So yeah, we have to use the copper layers in a smart way to design the PCBs for a reliable and high yield manufacturing process.
Great to know. Great to know all these details, because this is an area where a lot of informations have to be learned by the students who want to be the designer of a circuit in a PCB area. Because again, I am emphasizing that without a PCB, a chip cannot land up to an end user. So PCB is the main bridge after the chip that
Yeah,
goes to the hand of the end user.
yeah, yeah,
So
yeah,
that's great,
yeah.
great information. Another thing is that the next question I'll move over.
Yeah.
Could you please so one you have shared already, the copper area. Is there any thermal issues regarding the PCBs, or maybe it's in the manufacturing stage, or maybe in the testing stage, or maybe designing stage? Any checking related to the thermal effects? Maybe some cases, some ICs may get heated. Already we have the heat sink external, but in
Mhm,
case in the board level, in the PCB level, is there any thermal checks are done,
mhm.
or any precautions are taken for a long run, for a long sustainability with that
Yeah,
things are checked?
definitely at the design phase, there are used some simulators. Big companies like ANSYS provides us with high quality simulators for heat distribution. There are some even open source uh, simulators for that, or you can use simple mathematics and documentation by the manufacturer of the ICs. And I can say that, for instance, SMT uh, switching converter for your AC adapter, for instance, and those are typically SMT components with so-called exposed pad on the bottom side of the IC. And this exposed pad is used to transfer the heat from the IC to the outside. So you need to solder the exposed pad on the PCB, and typically those ICs are, or the, yeah, there is, because the heatsink typically is a very expensive component made out of copper or aluminum. Is expensive. So we can use the copper on the PCB. So you can design the polygon on the PCB that is used as a heatsink for that IC. And you can calculate the estimated effectivity of the converter. Then from the total power, you can calculate what must be the dissipation power coming out from the IC. And then you can calculate the area needed to radiate the thermal energy from the IC to the outside world. So this is task for us as PCB designers to calculate the area. But yeah, imagine that there are some tools, some calculators available on the internet or in the EDA tools. Even KiCad has some simple calculators for that. So it's not any rocket science. You can enter a few parameters, and the calculator will give you the minimal area needed to cool down to keep the temperature below the maximum level. So this is what we can influence at the design stage.
Great to know that fact. And I think viewers have a lot of information from you today on this session. We'll move on to the next question. That is the PCB layout designing is done manually, or there you use some automation or some algorithm, anything? Can you
Mhm.
share some light?
Yeah, that's another excellent question because these days we are in the AI age. Yeah, everything now is enhanced or improved with AI. Typically, traditionally, the PCB layout process is 100% manual, but the major manufacturers of the EDA tools like Altium or Cadence or Siemens are improving their systems with AI tools, which means those are, you can imagine a copilot in the PCB designer, PCB editor tool, and those copilots help you to distribute the components or routing the tracks on the PCBs. So yes, this is the area when the things are changing. I have to admit that the KiCad is not the tool that uses the AI yet, but I think in the future it will.
Yes, the AI has started to enter into the even the open source tool, as I have said earlier. Like the Audacity is a audio editor tool, uh, and that now I already have. I think a plugin called Vino that can actually introduces the AI inside the Audacity through a plugin. So I think in future it's not very far. I think something will be there by the developer communities. It will come inside the tool. So.
Yeah, I believe so.
Yeah, I think Audacity is only just 3.x version is now running, and with that version, they have included the AI into it.
Hmm
I
hmm
think there are two. I think two plugins are there. One is the for the noise cancellation. Another one is for uh, the transcripting process.
hmm
Sometimes people record meetings on audio recorder like Audacity, and they have to transcribe those things into and give to the office the transcribed details and
hmm
text, right? So those things are already, these two plugins are there with Audacity, not in the Linux version, but into the Windows version
hmm
right
hmm
now.
hmm
Audacity 3.x has that thing.
hmm
3.xx is the latest version. You can refer to its website. But I
hmm
think when KiCad has version 9, that means it has very much stable and matured up to version 9. So it's not a matter of joke for going of software to up to version 9. A lot of development has happened. I think maybe a couple of months or maybe couple of years. There, whatever is with the developer community, AI definitely
hmm
will enter, because
Yeah.
mostly now AI is entering into the field of text processing, audio processing, video processing, right? Which are mostly easy file formats, and slowly they will enter into the complex file format like. The Jarbor files and all those things that in the PCB design or inside the GDS2 files in the VLSI design. These are complex file formats, right? Have lot of data and lot of education has to be provided to the AI tool. So that is another side of the AI tool. It has to be trained with the data. So I think we are not very much far from the point. We will come. We will hope that something will come AI as a AI Copilot. I think you have, as you have mentioned, Copilot is already available in the GitHub, and in my channel, I have already made a video on Copilot and other things that are already there. I might have done that video 2 years back. So that time Copilot, at that time I think ChatGPT was not there. So
hmm
after I made the video, the ChatGPT came. I think maybe a year ago or so.
Yeah.
So Copilot
I
was much
cannot.
more earlier. Copilot was much more
Mhm,
earlier predecessor of ChatGPT. So because
mhm,
people, lot of people around the world use the GitHub for their codes and designs to be saved and present in a professional manner to somebody else in the other point of the globe. So I think there will be something that is getting developed for the KiCad. That's why I asked for the community, and people may be already working. As I have said, that the Linux Red Hat already have announced their AI version of the enterprise Linux, right? And SUSE
Yeah.
is also working on that. So first, the base things, right? The operating system will go support the AI development. Otherwise, the packages, the repositories like RPM, the EM, the .debian, all these things, right? They has to first
Hmm.
have to have the AI and ML enabled, and then things can go in a direction of the AI. I think for that, the movement has already started for Red Hat, for SUSE, and I think for Canonical, I think which is for the Ubuntu, right? They have
Yeah.
also started. All the base Linux repositories are now plunging into the AI.
Hmm.
Because AI
Yeah.
needs a lot of compute power, they will have to test it, and they have to first make the base ready, because on the base packages the softwares are built. So I hope the things the AI will come to the PCB design, maybe that will make the life easier for a
Hmm.
designer for the complex verification task they have to do for the
Yeah.
checking, etc. I think that will be very much helpful.
Hmm.
Um
Yeah. Definitely.
with that,
Definitely.
yeah, go ahead.
Yeah. 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 I just wanted to add because you lead me to an idea. I forget to mention regarding Ticket. All the major EDA tools, as I mentioned, Altium Designer, Cadence OrCAD, and the Siemens Expedition, are Microsoft Windows compatible only. You cannot run those systems on Linux or Mac OS. But KiCad is multi-platform. You can use it on Windows, Linux, or Mac OS. So this is great for all people in the world because not everyone uses Microsoft Windows. Yeah, we are using
Yes,
Linux and
yes, yes.
Apple devices. So that's perfect feature on KiCad because you can run it on every device.
Yes, yes. Every possible device around the globe. That is
Yeah.
the main thing. Even right now, one LT Spice series is it's a tailing part of the basic Spice, because I said like this is for the students who are just graduated or doing the graduation, and they will be going into the VLSI industry or the electronics industry. So the basic things is going on the Spice level, and there is the NG Spice, and there is LT Spice, which are included in the series. But
Hmm.
however, LT Spice cannot be used in the Linux. That is one main problem there. So KiCad being capable to be used in across the platform, that means if there are two users, right, one designs a thing and gives to the another designer. I am taking a hypothetical example. So one person has Mac, one person has Windows, and another person has Linux, but they can work concurrently with the files and they can exchange among them. So that is the main flexibility of the multi-platform softwares.
Exactly.
So that
Exactly.
that yeah, that is the very good thing to have, because and it also makes the software architecture flexible, right? And in any enhancement, say any plugin coming into Windows,
Hmm.
people will check whether that can be ported into Mac or ported into the Linux, and
Hmm.
that's how. And for Linux is a complex thing, because the OS is not like Windows. It's I think a lot of enthusiasts around the world, they contribute for the development, and the base has to be AI compatible first, like that I have said. Red Hat is doing it. If you go to the Red Hat page, official page, there you will see that Red Hat is doing, SUSE is doing, Ubuntu, the Canonical is doing, right? So all those Linux has stepped into the AI part, because the base packages has to be AI compatible. That means they will be able to interpret the AI and ML, right? So that the whole software can be there, right?
Hmm.
And as I have said, right, Audacity has two plugins. One is for the audio noise removal, and another one is for the transcription. So both plugins are in Windows. They have not been ported to the Linux versions yet. So Linux guys has to be wait. So
Hmm.
uh, for a multi-platform software like KiCad, you have mentioned, when a plugin comes, right, there will be demand to have that ported in all of the three, like Mac,
Yeah.
Windows, and Linux. So
Exactly.
that will be
Everything.
that will. That will helpful because in across the globe, see, somewhere people prefer Mac, somewhere people prefer Linux, somewhere people prefer Windows. Everybody has their own circumstances, maybe availability of hardware, maybe availability of the software, and everything. And there are techies who prefer sometimes Mac, sometimes prefer Linux, sometimes prefer maybe Windows. And these will be in future, I think, those developments on that level, and AI will plunge into all those softwares through the base
Hmm.
packages. Maybe on, I don't have the idea of the Mac, but Linux I have a idea, so I
Hmm.
can share. uh, and that's a very good thing to have the AI as a plugin, so that things will move faster.
Hmm.
I think
Definitely.
yeah, another software that coders use is a VS Code, which is again multi-platform. Although it's not a free and open source, I think it's from Microsoft. But people have multiple plugins for their writing codes. Even for Python, if you go and search in the library, there are a lot of co-pilot kind of stuffs are there that will help you to complete the code and
Hmm.
thing like that.
Yeah. You lead me to another feature of the KiCad, which is the fact that all KiCad project files, it means files for the schematic, PCB layout, or other supporting files, are text-based. And it might not sound like an advantage, but it's a huge advantage because when the files are text-based, you can use tools like Git or cloud services like GitHub or GitLab, and you can easily control versions of your KiCad files, which is not possible when using Altium Designer or other systems because those systems use the binary files, but KiCad use text-based files, and you can easily use the GitHub for control version systems. And majority, or not majority, but maybe not majority, but maybe half of my customers use GitHub for sharing projects with me. And we can easily track changes, yeah, version controlling, and all features available uh, in Git.
So that's the beauty. That's the beauty, that was I was saying. And you said about the text format, that is the ASCII format, right? The
Mhm.
ASCII format is very good. And that version controlling will be much more, because things will move in generations, right? So all those generations are saved in the version controlling systems like GitHub. That's a very good thing you added. And now I'll go to the last question of today's podcast. Is that
Mhm.
how a multi-layered PCB is manufactured, and what are the key challenges in making a multi-layered PCB? Even as a designer for you, even when there is a multi-layered PCB, like you have mentioned
Mhm.
earlier, there are layers in between, sandwich in between, maybe insulators, right? So.
Yeah. Those multi-layer PCBs are typically used in modern designs with very dense component layout, and when you need miniature dimensions, yeah, miniature components. Uh, so those PCBs are manufactured from the sandwiches. There is always a core sandwich, which is always uh, the let's say the sandwich for the central inner layers, and then those uh, those outer inner layers. It sounds strange, but yeah, you can imagine you can have 6-layer PCB. So the layer 3 and 4 is around the core. Then there is layer 1 and 2 and 5 and 6, and those are not around core. Those sandwiches are placed around so-called prepreg layer, and those 3 sandwiches, prepreg, core, and prepreg, are laminated together under big pressure and temperature in special machines. So those layers are firmly laminated without any possibility to uh, yeah, dismounting the PCB. So the modern PCB, multi-layer PCBs use very thin vias. It means the holes for interconnection. We can use special drilling tools out of metal or even the laser drilling, with the optical array from the laser, so you can drill holes even smaller than 0.1 millimeter and much less. So with those microscopic vias, there are as well the very thin tracks, much thinner than 0.1 millimeter, and the clearance or the distance between the concurrently running tracks is getting lower as well. And when there is not enough space between tracks, there is always danger of short circuits, yeah, because the process is chemical, the etching process, so you need to get rid of all the copper in between tracks, and when the process is not perfect, there are some residues of copper that can make the short circuits. So those are the biggest, I think, uh, risks when manufacturing the multi-layer PCB, because the clearance distances are very thin and the openings are very small. So those two things require the modern machines, but major PCB manufacturers can easily produce up to 32 layers PCB without any issue. So one thing is that you, as a PCB designer, you need, when you're designing such a dense, high, let's say, integrated PCB, you need to work with the PCB manufacturer from the day zero of your PCB design, because literally, you design the PCB to be manufactured at a PCB manufacturer facility. It means that it's not like vendor lock, not at all. But you need to know the possibilities of the PCB manufacturer, the minimal track width, the minimal clearance, the minimal diameter of the vias, the minimal diameter of the THT, the distance between the tracks and vias, etc. A lot of parameters. And your PCB manufacturer can be good with drilling microscopic holes, but not so good with the thin tracks, or vice versa. So you need to check the possibilities, the manufacturing possibilities of the manufacturer, and include those numbers into your EDA system, because the minimal numbers cannot be like, yeah, you can't go below the minimal numbers naturally, because otherwise the PCB wouldn't be manufactured at the particular manufacturing site. So it's a complex process, but it's not a rocket science, as I said. It's about communication. It's about gaining information from the internet and getting things together in a natural way. So we, as engineers, can do it, and it's a very straightforward process.
Great to have all these basic informations that if any electronics enthusiast has uh, in mind of designing PCB or choosing the career as a PCB designer, that person has to get knowledge and lot of basic informations, advanced informations. They will come to know one when they work, right? The working knowledge, but basic knowledge you have shared in today's podcast. So that is a very great. Uh, from Tech Simplified TV, I would like to say that we are very much lucky to have you today in this session. And Peter is well known as the KiCad guy, and he has his photo with his headphone, red color headphone mostly, and that photo I have also used in the thumbnail. And anything you would like to add apart from the questions from your side? Anything that you want to share about you that you want to share?
Thank you for having me here. I think I cannot add more. I encourage all your listeners and followers. You can visit my profile. Please, if possible, put the link to my profile in the
Sure.
bio of the video. Yeah, so you can feel free to visit my profile, and you can follow me on LinkedIn, and you can get every day you can get one post with some interesting information from the PCB design world, from my world, from my job. Yeah, I share details from my projects, etc. So yeah, this is what I want to add. So again, thank you for having me. It was a great hour with you, and I had a great time.
Yeah, we had a great time with you, Peter, and all the electronic enthusiasts. I think they either watch this live or they will see a replay once this recorded version is there. Right now we are live. Maybe sometime later they will get the recorded versions too. People will watch, and I think people who are enthusiasts maybe want to know about the PCB, and you have shared a lot of basic information about the PCB. So these are basic know-how things. Thank you for coming to the podcast, the Semiconductor Podcast. It's a dialogue-based podcast. So thank you, Peter, for coming.
Thank
And
you.
viewers will be offline right now after having this session. Thank you, Peter, and I'll put Peter's LinkedIn profile and his details in the video description so that people can pick up. And if they want to connect with Peter, they can connect from that. Okay.
Thank
So bye
you.
bye, Peter.
Thank you.
Bye.
Bye bye.
Bye.